Thank you, everyone, for coming. I'm Alice White. I'm apologizing that I need to wear a mask, but I'm protecting all of you.
Alice.
I need to use the mic. Mike says I need to use the mic. Is the mic on?
Just get up to it.
Yes. Uh-oh. Okay, how's that?
Just get right up to it.
I have to get right up to it.
Do you
All
want
right.
to use the podium so I can push this toward you?
That'd be great. All right, thank you. How's that?
Is it?
So first, I just want to thank the Middlebury Energy Commission for sponsoring this workshop. And a big shout out to Mike Roy for the Grateful Dead inspired poster. Thanks to Mira and Mike here at the church for all of your help. And I also benefited a lot from Jamie Hand's experience with an earlier workshop. So the genesis of this workshop was actually a tour sponsored by Debbie New of the carriage barn in Shelburne Farms. Steve Smith spoke that day, and he was peppered with questions by the audience. So as a relatively new transplant to Vermont, I was under the impression that the state was way behind Massachusetts in particular in the uptake of this technology. But I learned from Steve of the many geothermal projects that he has built in the Burlington area. Steve mentioned George Martin's contributions to that project, and since then I've heard his name again and again and again. So with the urgency of, thank you, that's right. And special thanks to my Middlebury Community Television tech guy. So let me just start again with the urgency of reducing greenhouse gas emissions. Because of the superior efficiency with respect to other heating technologies, interest in geothermal is really growing in Middlebury. So over the last year, projects including elderly services, the library, Stonecrop Meadows, and the college's Stewart Hall renovation have been started or announced in Middlebury. So I thought it was a really good time to do a deep dive on this technology. And you can just imagine my delight when Steve and George both agreed to come to Middlebury to kick off this workshop. When I left Boston 2 years ago, my institution, Boston University, had just adopted a really aggressive climate action plan. Actually, they went to the board with 3 plans, and the board adopted the most aggressive one. The year I left, they completed work on what is the largest geothermally heated and cooled building in Boston. And let me just show you a picture of that. We call it the Jenga building.
Whoa.
It's 19 stories high, glass enclosed, triple glazed glass enclosed building, 345,000 square feet. This is 3 times the size of Bicentennial Hall on the Middlebury campus. 31 to 1,500 foot boreholes underneath the profile, right in the middle of Boston. So I just share that with you as kind of a aspirational thing to think about the scale of what is possible. So let's get started with the first speaker, George Martin. Grew up in Middlebury, I understand, and he studied engineering at UVM. After his sophomore year, he was flipping through the phone book and found an LN Consulting, had an engineering internship there, and upon graduation went to work there. And 20 years forward, he's now president of LN Consulting. LN Consulting does building design solutions focused on health and sustainability, specializing in analysis and technology, and they collaborate broadly with their clients and the community. So let me go ahead and pull up your slides, George, and you can come on.
I guess we don't need this slide, because that was such a good job of making it through.
That's a little bit more detail. So let's just see if I do this.
You should just be able to press enter.
Okay, and now I just need to do one more thing, which is over here. Okay, thank you.
All right, maybe I should just leave this. All right, see, this is what happens. There's a timer This always happens to me. Maybe if I,
There's the back, down here is the back slide thing.
yeah, just if I go, oh, we'll see. We might just move forward, it's all good. All right, so we're here to talk about geothermal, but geothermal is really not possible without heat pump technology. So I just wanted to kind of give a general overview of a heat pump and how it differs from maybe like a boiler, et cetera. So heat pumps are a mechanical piece of equipment that are used for heating and cooling of a building. I think the key component is that heat pumps are transferring energy from a source to a load versus like a boiler, it generates energy. So what that means is that when you're heating a building, you're basically absorbing heat from a source, which could be air or water or the ground, and you're transferring it to that building. When you're cooling, you're actually rejecting that heat to that source, the air, the ground, and in order to cool the inside of the building, if that makes sense. So we have air source heat pumps, which are heat pumps that you have an outdoor piece of equipment. You're using that outdoor air to heat or cool a building. And then we have ground source heat pumps or water source heat pumps that use water to transfer that energy to heat or cool a building. So just going through a conventional water source heat pump versus a ground source heat pump, which is what we talk about with geothermal. Basically, in a building, you have a bunch of heat pumps located throughout the building, which is similar to you have a thermostat on the wall. This heat pump will heat or cool just like any mechanical piece of equipment. But on the other side, the source side, we'll call it, there's a loop that connects through the whole building. So there's water that circulates through this whole building, and when one heat pump in the zone is calling for cooling, for example, that loop gets heat added to it. When another zone is calling for heating, you're actually taking heat away from that loop around the building. And the cool thing about heat pumps is that you can share energy through a building. So you can share energy if one, for example, if you have some solar gain in the morning on a portion of the building and it requires cooling, but the other side of the building is shadowed and needs heating, you're really sharing that energy through this whole building loop. When I think Debbie will talk about thermal networks, that also can be scaled up to multiple buildings, right? So heat pump technology allows us to kind of use waste heat, transfer energy throughout these big loops, and the goal being ultimately to reduce your source. So the source on a conventional water source heat pump is a boiler, which as this loop cools down, if there's a bunch of units in heating mode, you add heat through this boiler, right? So you're generating heat from a fossil fuel or electric resistance. When it gets too hot, you actually use like a cooling tower or a dry cooler to cool that loop, reject that heat to the outside so you don't overheat that loop within the building. So when we talk about thermal networks and geothermal in general, we model these things to see, like geothermal in general is an expensive technology to drill, so we try to model these to reduce the overall source, which is that ground source portable field. So the nice thing, just to add to that, so this transfer of energy, when we're talking about a boiler generating heat, it's usually about 90% effectiveness. So like for every unit of energy you put in, you're getting 0.9 energy out. Electric resistance heat is 1 unit to 1. But when we're talking about heat pumps, it's actually up to 4 to 1. So that's where you get this efficiency out. It's that transfer of energy is a super efficient process. Just wanted to go over a couple different things of heat pump technology, obviously geothermal versus air source. So air source, great way to electrify a building, not knocking air source, but it is dependent on the outdoor air temperature. So you can always imagine that when you're trying to cool a building, it's the hottest outside, so you're trying to reject heat to a very hot space, and then when you're trying to heat it, it's very cold outside, so you're trying to absorb that heat from 0-degree air. You can imagine that's not a very efficient process. If we were in San Diego or something and it was 70 degrees all the time, it's actually probably a pretty good technology to use there, right? But up here in our climate, we have like the worst case and on either end of the spectrum here. So geothermal offers that consistent ground source temperature, that 50 degrees, which is why it's super efficient. Air source, again, has outdoor components that, pollen, dust can get caught on that coil that is supposed to reject to the outside. That can foul the heat exchanger and reduce efficiency of the system, so that just has to be cleaned. Whereas ground source, you don't have that. It's all a closed system within the ground. and a closed hydronic loop. And then the other thing about air sources, you do have high pressure refrigerant piping from those outdoor units into your indoor units. So again, those can leak, and there's new refrigerants out there that are flammable. So just a little more consideration that needs to take into account there. Again, not knocking air source, there are some considerations to take. It is definitely less expensive to install. Geothermal versus conventional water source system. Again, central boiler is needed for this, so instead of your heat add through a boiler, you can use your ground loop to add your heat, so you can reduce fossil fuels. And then a cooling tower, there's a lot of maintenance and water usage for that, so again, the geothermal, from a maintenance perspective, is very effective. Just to when to consider this stuff, new construction, always worth looking at geothermal. Any existing construction with a big program change where you're going to change a bunch of mechanical components, always worth looking at that. And then obviously any construction where there might be a central piece of equipment that is going to be changed. Like we did a project at Rutland Regional Medical Center where they had an old cooling tower that needed to be replaced. And we just said, hey, wait, let's take a step back. That was a conventional system with a boiler and cooling tower. And we said, well, let's just look at geothermal here, because you're going to have to make this big capital investment on the cooling tower. And with the incentives, it actually worked out very well. So we were able to convert that conventional system to geothermal. So anything like that, if, before making a big investment, capital investment, always worth, I'm not saying it's always the best solution, but it's always worth just taking a step back and taking a look at that. So just going through a couple different types of systems. So we've done all of these systems. I would say that the most common is closed loop, which I'll talk about here first. So closed loop geothermal is fully closed hydronic loop. So basically, as I was talking about, all these heat pumps in this building, heating and cooling, instead of that boiler and that cooling tower, you literally are just circulating water down through the ground and back up, and that heat exchange, that conduction with the earth, is what heats or cools that loop. So really simple. It really is just, there's no moving parts besides that fluid going through this borehole. So you have multiple boreholes. Again, you exchange fluid down, and that's really it. As your loop cools down or heats up, you just throw it down to the boreholes. The downside of this is that it's a little more costly because you're relying on that surface area. You need surface area to reject that heat or absorb that heat from the ground. So for big buildings, this could require a lot of boreholes, which again are expensive. You basically have to drill a 6-inch bore, 500 feet or so, depending on your design. You put this U-bend HDPE pipe down, and then you grout it, and you got to test it. And there's a lot there, right? So again, when we're looking at these systems, it's important to model these systems, understand the loads of your building, balancing these loads to optimize a system, because this is really the expense of your system. The interior stuff is all the same. Like, there's not really a difference between multiple mechanical stuff. It's the exterior portion which can get expensive. So that leads me to the next open loop. So we've done a lot of open loop, actually with Steve as well on many projects. This is like, when we do a test well and drill and I find water, I get very excited because I know that we can have a low cost solution potentially and use a ground source system. So this system is advection, it's called. So basically you're using a fluid, so the fluid flow and temperature determine your capacity. So rather than having the surface area determine your capacity, you're literally dependent on how much water you can produce from a well. So in this scenario, just like a traditional well pump, like if you had one at your house for domestic water, but we have up to 250 gallons per minute we've done, and basically just circulates water up through a heat exchanger and then just puts it right back in the ground. So you get this constant 50-degree water that you're circulating up, and that's the means to add heat or to reject heat from that central loop that we're talking about to heat and cool the space. So the nice thing about this is, like, you could have one well that produces 100 gallons per minute or something, and that's it. You don't have to have 20 boreholes, right? So this is exciting when because it's a low investment cost, and could actually be lower at Hula. I think it was actually lower to do this system than it was to do a conventional boiler cooling tower system. So like and this is Chamblee College, the same thing. You're having a big central plant that you have now, again, an investment on a boiler and an investment on another piece of equipment versus a well pump. You can imagine that's pretty low cost. And also super efficient. You do have to take into account injection back to the ground. So pumping energy is a big concern over time. So we do testing, inflow testing. We'll hook up a pipe to a hydrant and push water down to the aquifer to see what the back pressure is, because we have scenarios where there's just too much back pressure and the pumping energy just doesn't work out. We model it, and the energy used to actually try to get it back in the ground is not cost effective. So there's ways to get around that with more injection wells, or what I would do is this type, and we're actually doing this at a hotel in Winooski right now, which is a standing column well. So this is kind of a combination of closed loop and open loop, where you use conduction and advection as the energy transfer method. And so you pump out, it's basically like a straw. So inside the straw, there is a well pump, just like the open loop method, which you pump into the building through a heat exchanger, and then you actually inject it back down to the same well. But you inject it at top, and the straw has an opening on the bottom, obviously, so you're basically using the heat exchanger, the water flowing all the way down this well and back up this straw. So it's almost like a recirculating borehole, if you will, but you use that fluid transfer and the energy transfer with the ground, so it's that conduction and advection. And what happens is over time, you do have to bleed. So over time, just like your building loop, you'll have it'll get too hot or it'll get too cold. So then there's this little bleed that you would do, and it would just go into another injection well. But the nice thing about that is it's a lot less flow than a full production injection. So usually when we see these things, okay, if we're injecting at 100 gallons per minute, say, and we had 25 PSI back pressure, that wasn't great, but when we only need 5 GPM of back pressure, it's negligible, right? So these are just, there's always a solution, but it's just finding that right solution, which can be difficult, and finding that most cost-effective solution, I guess we could say. And again, there is, every well, we do water testing. I mean, it's possible that you have a very bad well where there's, too much debris or something of that nature, and then, open loop or standing column may not be the best solution. But when we do find that water, that's good water. It's pretty awesome, and really a great way to get a geothermal system installed. So a little bit, talked about this a little bit, but right now we have 3 full-time energy modeling people in our firm, and I can't emphasize enough, like data, that's what we're all about. I mean, with geothermal especially, if you over-design this stuff, it's just never gonna be cost effective. So we know that, especially with cost now, everything's very expensive. So we work with architects to kind of develop envelopes, because that's important. Yeah, we are all mechanical, electrical, but it's all based on the architectural envelope. If you have a bad architectural envelope, the mechanical system cost is gonna go way up, building cost is gonna go way up. So, and sometimes it's the opposite. Maybe if it's over-insulated, you have a cooling dominant building and you realize, wow, we're really low in heating, but the cooling load is twice or 3 times as much as the heating load. That's not great either, especially if we're actively cooling. We see a lot of this in passive house applications where, yes, it's supposed to be passive house, so you're not supposed to be actively heating or cooling, but you are, especially in commercial applications. And we find that these buildings that are super insulated are great, but they are cooling dominant. So if we're just heating them, not a big deal, but we also obviously are cooling them now these days. I think when we started, we were only heating buildings, but unfortunately, we've gone the other way as well. So it's just important to understand, energy recovery for ventilation. There's indoor air quality things to look at, and just holistically look at the building. We're not just the mechanical, people in a box here, and then the architect does their own thing. We work holistically as a team to come up with the best solution, which I think is really what makes the most sense. And this is data. It's life cycle costs, so there's initial costs that could be lower, but operational costs and maintenance end up being a lot higher. And then there's a middle of the road maybe where you're using some fossil fuels, but again, you have a slightly higher initial cost, but you have full indoor air quality and heating and cooling. And then there's maybe the geothermal option where it's a little higher cost, but you have no fossil fuels, and operational and maintenance costs are way down. So these life cycle costs based on the energy modeling help us give the clients information to make the best decisions for them, based on their energy goals and project budget. Just to touch on this, so this is only for closed loop. The nice thing about open loop also is that you do a model and say you have 100 tons of cooling required, it's based on flow. So as long as you have that flow, we don't need to worry about balancing loads or anything. It's just, that's it. With the heat exchanger, the ground heat exchanger, closed loop system, it is a finite load, right? Like, you can only transfer so much energy in the ground before it heats up too much or cools down too much, and then it's no longer effective. So you do have to consider balancing of loads. So we use the energy model and then plug our borehole field into this ground loop modeling program, and it gives you, like, you can say, okay, what is this looking to look like over 50 years? And it'll say, okay, well, your temperatures are this, and then your ground temperature raises by 2 degrees. And so you can optimize this over a certain period of time and maybe reduce the borehole field, or maybe you decide that it's cooling dominant and you say, well, we're just gonna add a small cooling tower for those times where we need to shave off that extra load or something like that. So it's a little more in depth, and this is like really for big commercial buildings. A lot of times for residential, it's pretty straightforward. There's not like a lot of different loads we have to worry about. It's heating or cooling, and it's a pretty simple program space. But when we talk about big buildings where there's server room or all this other stuff that we have to consider, this is just an important way to ensure we're on the right track. Again, just wanted to go over a couple different options of heat pumps. So this is probably the most common heat pump. It's basically like a furnace like that you'd have in your house. Looks like it's just a big box. It has all the compressors in it, and it has an air side component. So literally, it connects to your hydronic loop, your building hydronic loop side, and you're just heating and cooling air with this box. And it can be installed like vertical style here, or horizontal in the ceiling, or it can be concealed in the ceiling, and you just duct to the space. Pretty straightforward. Probably the most common we use. And things to consider. Just you want to be able to access it, and there is a compressor in there, so there's some noise that you just want to consider. But we've installed this exposed in spaces, and without any issue. Vertical stack. So when we've done some skyscrapers, this is like what we kind of use. This is again, water source heat pump, so it can be used for ground source geothermal or just a standard conventional heat pump system. These are cool where you have high rises that are all kind of in line, all stacked, and you just literally, they just sit in the wall. They're ductless, you can duct them too, and then there's just a set of pipes that kind of goes right up, the 20 stories or whatever it is. Just a very cost-effective option for like residential multi-story. And we actually are doing this right now in some residential in Vermont. Water-to-water heat pumps. So this is where you have the water on one side and you can create hot water, chilled water. So we do this a lot of times when we're usually in a retrofit application where there's already a hydronic system in the building and we need to provide heat to that. A lot of residential applications where there's already kind of a baseboard or an underfloor radiant loop just gives you a way to convert to an all-electric geothermal system without kind of redoing all of your internal components. You do have to consider the lower hot water temperature, but usually with envelope improvements and with some air sealing, et cetera, we can make that work. And a lot of times we found that a lot of those systems are over-designed in the first place. So they say they're rated for 180 degrees, but there's actually enough capacity for the lower 120, 140 degree water. And you can use them for domestic hot water heating applications too. But it just gives you another way to use geothermal to heat and cool. So there's just a lot of options. And the final option, which again, we do not do a lot of this. I did this in McDonald Hall, and I think it was maybe two of these geothermal. One was McDonald Hall, and it was a historical building with like no space. So this is basically an air source heat pump system, kind of those components. So instead of the outdoor unit, you have an indoor unit that's connected to the geothermal system. But the nice thing about this is they have a bunch of ductless options. So, those standard cassettes you see, I know they're not the most aesthetically pleasing, but in scenarios where you just have no space, sometimes it's the only option to heat and cool those spaces. So we were able to use, the fan coil units are only like 9.5 inches versus 20 plus inches, and then again, there's ductless systems. So kind of a cool application. Again, don't do it a lot, but just showing how many different types. Geothermal can really kind of be implemented in all the types of mechanical systems out there as far as the internal components go. So it's kind of neat that you can use all these different pieces of equipment all at once, or hybrid, or whatever approach you want to do. So a lot of flexibility.
Because I'm sure George will take questions, and I actually have a couple to start out with.
Okay.
I want to, I'm going to speak fairly loudly, so I don't have to use the mic. I just want to emphasize the idea of sizing the system properly and how the modeling is extremely important. When we decided to install a residential geothermal system, the initial estimate came in for a system that was twice as large as what we ended up putting in. And so my first question to you is, why is it important to size the system properly with a ground source and heat system?
Really, well, if you're oversizing it, it's cost. If you're undersizing it, it's not going to function at some point in time. So, again, that's where the modeling really comes in. And I think in the past, there's been a lot of, whether it's contractors or engineers who weren't modeling, and they were just using kind of rules of thumb, like, 200 feet per ton or whatever, and that's just not, you might be able to get away with that, but it's just not the way to do it when you're talking about especially more complex systems. And it all is based on an envelope, right? Like if you have a really tight envelope, or if you have a retrofit that may be leaky, it's just not. You just can't do it that way. So, I always model this stuff. There is a cost to that, obviously, but there's a real big cost if you don't get it right. And also, again, on the initial standpoint of, I think people that are oversizing, we can't do that anymore. It's just going to cost too much. So. Unfortunately, we're out of the point where we can throw in two or four more boreholes and be fine with it. It's just, those are expensive. So the only way to really push these geothermal technology forward is not doing that. And I think there's been a lot of negative maybe press on that, because I think there has been some over designing, which is driving the cost up. So we're trying to push back on that and show that it is feasible. And I think there's some questions on, are there projects that are doing, like multifamily projects that are doing geothermal? And yes, we're doing a few right now. So there's affordable housing projects that we're actually doing. So if those numbers work for the affordable housing, then that it's probably going to work. Because they have tight margins. So it does work. And it's just, again, making sure it's designed appropriately and you're not over-designing and stuff.
Yes, go ahead.
As probably most people here know, this is a field that the technology is rapidly evolving. How do you, as a company, keep track, or what are the resources that you go to vet new technologies before you adopt them? And how do you confirm that the technology you're picking is robust?
Yeah, so we've been so first of all, geothermal technology, I think Wake Robin has one from the 90s going on, and heat pump technology, I know I've worked on one from the 80s, like water source heat pumps. So this stuff has been around for a while. R22, now we're on R32 and R454B. So there's been like 3 refrigerant changes since I think it started. But yeah, there's a lot of technology out there, and I would like to say that I was perfect in vetting out everyone, but I've been on the bleeding edge, if you will, the leading and bleeding edge of some of this stuff, which as an engineer is good. Sometimes it's the only way to learn, honestly. And we fix the problem, obviously, and find a solution, but some of my best projects or most rewarding projects are probably the ones that are most frustrating, because I had to really dig in and really understand the technology, and that's actually helped me be a better engineer, right? So I think, you have the salesperson who's like, this is what it does. It's all, and then you're like, okay, that sounds good. And you have to try it. It's like, this seems like it's the best solution. And then you realize there's these little things that, that, you didn't tell me that. And then now, so we try to, vet out these things as much as we can. But yeah, there's sometimes that we do push the envelope as a firm. I'm not gonna design around this huge building, but if there's a smaller project that I can, know that if something really goes south, I could still remedy and make something work that'll be a great system for the client. I will look at new technology, and also I just have that conversation with them, like, hey, this, just so you know, it's the first time we're doing this. But usually the technology's been out there. It's just like there's a tweak, right? There's, okay, now this can do simultaneous heating and cooling, so we can improve efficiency or whatever. So I would say the biggest exciting thing that's in the field is the CO2-based refrigerants that are happening, just because it looks super efficient, and they can create high temp hot water pretty efficiently, which for retrofits and for big college applications, that's kind of exciting to see. But Yeah, I mean, I like I said, I would like to say that every project I've done has gone smoothly. It's not that, I mean, there's always something, and we just designed making sure that we know we can have a solution that's gonna work. And it's mostly just like getting controls figured out, you know, stuff like that, but.
But is there a source that you trust that you can go that evaluates different technologies as they come on?
I mean, like I'll work with manufacturers directly. So like we'll just go test something and I'll ask questions and I'll go to a plant and say, okay, what's this? But there's no like, there's no real source out there. It's mostly just researching and you know, doing it yourself and taking it upon yourself. I mean, again, there's a lot of sales guys out there that they'll say something and you're like, okay, that sounds promising. And then you kind of go and ask questions to the manufacturer and kind of, again, see all the things that we've come across in the past that could be problems. And from there, you can kind of make your own decision. Like, there's some systems I'm not necessarily gonna mention, but I would never use just because they're not ready yet. Like maybe in 5 years, but like, I kind of questioned the vendor and I'm like, why didn't you do this and this? And I'm like, okay, this is not gonna be a good system. So, you know, it's usually just, if they can't answer some simple questions, you know you're probably not on the right product. But yeah, we work with vendors really to understand that.
Totally.
So, ground source heat pumps are often talked about in a heating and cooling setting, but one of the ways that the frontier is being pushed somewhat is in using water heated in an industrial process. And I'm curious, perhaps if you could jog my memory of what is sort of the upper temperature range for hot water that can be produced and how that might potentially be applicable in an industrial setting.
Yeah, so I think I'm not totally familiar with like direct use geothermal, which is like, you know, actual tapping into the Earth's thermal energy. This is like a heat exchange or water-based system.
Sure.
So I'm not sure if that's what you're referring to. Like that's where you have like power plants that you're actually taking like steam basically from the Earth. But as far as like, you know, you can,
With these particular systems.
Yeah, with these systems, the hot water side, you can get up, there's technology you can get up to 180 degrees. Now it's not efficient, right? So like when you can imagine if you're trying to take something from 50 degrees to 180 degrees, there's a lot of energy that you need to do that. When you're like, so when we were designing this stuff, it's like, well, maybe design for 120 or 115, which is what a lot of the standard refrigerants, that's kind of their sweet spot operation range. There's other refrigerants that, you know, allow for the extension to that higher range. But again, it's an inefficient process to do that. Just because of that delta T that you have to make up. So when I'm designing systems, and I was doing this before even geothermal, like for example, a boiler. If you have a condensing boiler, it's more efficient at a lower temperature because it allows for that condensing to happen. Whereas if you design those systems at 180, your efficiency goes way down. It's like more like a conventional 80% boiler. So like those things are, it's just like good design standards, and the nice thing about that is all the projects that we've done that, now actually they can get converted to geothermal pretty easily because we've already thought about that low temp operation. So it's one of those things where you design things at the worst case scenario, like doesn't seem like that makes a lot of sense, but as far as yes, there is an opportunity to get to those higher temperatures, but we would never design around that unless there's a technology that comes out that is super efficient and it doesn't matter, right, for some reason. But,
So the boreholes, construction creates disruption. So what kind of disruption when you're, like, say you were putting something in downtown Middlebury, how disruptive would that be?
Yeah, I mean, we drill in Burlington all the time. It's loud, and when we drill like outside of like sensitive spaces like hospital or something, you know, there's ways to mitigate that noise. But yeah, I mean, you need to have space to get this drill rig in, and you're drilling for a day to maybe half a day for a borehole, and there is some noise and there can be some water, so you have to make sure you dig trenches to get, if water comes out, fluid from the drilling process, you kind of have to dispose of that and make sure that you know, it goes to a drain somewhere, storm drain or something, or you just have it in a big pit and pump it to like a frac tank or something. But it is, I mean, it's not noisy, but it's a temporary process, and we've never had an issue. The only time we had an issue actually was we were going to go geothermal on a project, and there was a historical building, and we started drilling, and the vibrations actually were causing disruptions because we had a limited window, we had to go kind of close to the building, and they were actually hurting the foundation. We saw like potential issues. It didn't actually overall do anything, but like that's when I think the disruption happened. But other than that, if we have space to drill a little further away from the building, yeah, we do it in cities all the time, so it's not a big deal.
Yeah, there are at least 2 projects in downtown Middlebury. The Ilsley Library boreholes have already been drilled, and elderly services also drilled. And actually, our home is on a 1/4-acre lot where we drilled there, so our neighbors haven't complained.
Well, it's only temporary, right? It's not like it's a year's worth of drilling. If it's a residence, it's a couple days maybe, so.
It's a days of entertainment too for everybody in the neighborhood, so. Can we just ask George about maintenance of ground source heat pumps versus air source heat pumps?
Yeah, I touched on that a little bit, but basically, kind of what I was saying, all the inside stuff is pretty much the same as far as the units. You have a filter that you have to change, right? So it's like any air filter in a furnace or cassette unit or some kind of fan coil unit. There's something that's recirculating air, heating, cooling space, and it's just a filter that you have to change. So that's kind of any system, unless you're talking about like a baseboard hydronic system. Any air-based system, you have a filter. So that's everything. And then, really, that's kind of, on the geothermal side, you're just circulating water through a loop, and yeah, you want to make sure that you have the appropriate chemistry in that water initially, but really, once you do that, it's all closed, and there's just you're not in contact with any outside source once you kind of do that. So that's why it's super efficient, but also super low maintenance versus, like I said, an air source system where you have this thing outside that is circulating air to kind of reject or absorb heat, and when there's pollen out or whatever, things get caught in there, leaves, and then you got to make sure that it's clean, or if you don't, you're going to have less transfer of energy, and then that compressor is going to work harder trying to heat and cool the space, and eventually it's going to fail. So like we've seen, that's the biggest thing that we've seen on these air source systems, like in multifamily developments, that you throw 100 of these things on the roof and they're just never maintained or not maintained enough, and next thing you know, they fail after 7 years or something like that, and you're like, okay, well, that's a lot. that's not what I was hoping. I was hoping to get at least 15 years out of these. So I think that's, if you maintain these systems, and that goes for anything, like the longevity of the system will last, but as you know, now it's tough to find, it's tough to have people that find people that can maintain those, or just have the time or cost to do that. There's a cost associated with that. So it's that balance of how often do you have someone come in and clean the coil versus, what could potentially happen, a premature failure or not.
With regards to maintenance, what's the stability of the wells in their life?
Yeah, so they claim, the piping itself is warranted for like 75 years, and they claim it's way over that. I'm not 75 years old yet, so I don't know that for sure, but the idea is that they really are there for, we've seen some failures in the past, like there has been failures on systems, not systems that we've designed, but systems that were installed before, early, and I just think that they weren't properly tested, and there's a testing and kind of quality assurance that needs to be done to make sure you don't have leaks, to make sure, again, that you kind of flush the system, but now all the well drillers are pretty competent in that, but I think they're, decades ago when it was kind of new, there's just things that were a learning curve, and I have seen some failures as far as leaks go, and it's usually at the wellhead, borehole head, where because the U-bend is typically all one fuse factory piece of it, so you just throw it down there, and then at the top is where you have to fuse it to the horizontal piping. So usually that's where you would see a failure, at those joints where the contractor has to fuse it. And luckily, those are usually in places that can be accessed, and you could dig it up. And yeah.
What about open loop systems?
Open loop systems, the biggest concern or issue we had was just a pump failure, but that was after 15, 17 years. So yeah, we had, which is normal. That makes sense. But there's definitely a little more maintenance involved with that. We have, the heat exchangers themselves. You could pump directly through the heat pumps. I don't like doing that. I like to separate the open loop side from the building side, just because any contaminants get in there, that's a big nightmare. So we have heat exchangers that you pump through, and technically those heat exchangers over time can foul up just like an air source component over. We haven't really seen that actually, but you can just clean those. So there's a maintenance protocol, and we usually do redundant heat exchangers on big projects. So, if you have to clean one, you can still operate your building. But
in terms of residential retrofits, what types of homes make the most sense, have the most best properties, most practical versus ones that don't make sense?
yeah, I would say one, it'd be nice to have a pretty tight building. Steve did a retrofit on his house. He can probably speak to that a little bit. But it's nice to have a tight building. That's the way things are going to be most cost effective to reduce your overall load. It's nice if you could do an air-based system, and you have hydronic baseboard that you can heat at the lower water temperatures. Otherwise, again, you're kind of like a house that has radiant floor heating, for example. Perfect house for geothermal because that operates at a low hot water temperature. So you just that's like when I see that I'm like, okay, this would be great. The downside is that if you have cooling, it means you're either putting in another unit, a water source heat pump that also can heat or cool, or you're using chilled water off that water heat pump, which I just don't like to do in a residential application. Chilled water, first of all, there's a switchover that has to happen. It just gets more complicated, but you can't do it. So in Steve's house, we actually just had, for partial cooling, we put in a water to air heat pump and a water-to-water heat pump, which is nice because, again, cooling, you don't need to be perfect with all your distribution. It's kind of more of get it out there, it can recirculate, and it's not as temperature specific, whereas the the heating is. So we kind of were able to snake some ducts through the house, or Steve was, I didn't do that, and make it work and get the cooling where it needs to be, and then use that through the shoulder seasons, and then that water-to-water would kick on for the real heating during the winter. That's and you have a wood stove too, so there's a lot of options for Steve. But yeah, it is case-by-case basis. I would say that if you had an old leaky house, it's probably not the best application until you improve the envelope. But other than that, if you have a good envelope, then or improve it and seal it, there's no reason why it couldn't work.
Do you have a rough rule of thumb for comparing sort of lifetime system costs of a new system, say for residential purposes, versus something like all sort of air-based heat pumps or any other more conventional system?
Yeah, we've modeled this a lot as far as what does it cost. Usually it's 20 to 30% more, but that's where the incentives, that's kind of why they have the incentives at that price point, is to bring that cost down. We found it's 20% more in residential, especially I think the biggest hurdle is that when you're looking at geothermal for your residents, you have two contractors, typically. There's some stuff like Dandelion companies that go in and maybe do the whole thing, but typically you have two different companies, and I think that's one of the biggest hurdles I have, at least for residential. We do a lot more commercial, we don't do a ton of residential, and if we do, it's a bigger project where you have a GC and a bunch of contractors, so it's the coordination is already kind of in place. But if you have a contractor that's coming in and saying, hey, I want to heat and cool this building, okay, air source heat pump, easy. They can do the whole thing, give you a price, done. I think the challenge is finding that, bridging that coordination where, yes, you need to have a sub, a well driller, to come in and pipe up to your mechanical room, and then from there, they take it and do all the ducting and piping, and it's not overly complicated, but again, it's just that other step, which is challenging when everyone's busy anyways, and you're familiar with a certain technology, and it's just another thing. So typically we don't see it installed in residential unless the owner is I want geothermal, we need to pursue this, and I have ideas on how to change that, but so far it hasn't gotten anywhere.
Is that 20 to 30%? Is that just the upfront costs you're referring to,
Or the life cycle?
Oh, the payback is typically with the incentives. I don't know, it's 8 to 12 years we've seen it typically. So with the operational costs and the lower operational costs and lower maintenance, it's 8 to 12 years typically. Yeah.
That's for air source or ground source?
Ground source versus basically any other system.
Do we have time for one more question?
Actually, I've got someone
Oh,
back there.
yeah.
A simple question, can you do multiple residential houses off one well?
Yeah, so if you had, probably not one well as far as a closed loop system, but if you had one well, like an open loop system, which would probably be a couple wells, and then the question would be, do you want redundancy? But you could technically, if you had enough water, you have one well that produces and can circulate to all these different residential houses and back. We actually have that at Hula and Chamberlain College. We have multiple wells for redundancy, but those wells heat and cool multiple buildings. So we have, I think at Hula, which is a office space tech hub in Burlington. I think it's like 140,000 square feet or something, a couple buildings. We have a third building potentially to connect to too. We have, I think, 3 production wells and 4 injection wells, which one well typically takes care of all that for the most part during the year. So.
All right, go ahead, one last question.
I love the sort of optimization of the load calculation to meet demand, much more along the European lines of design. But buildings change and building use changes sometimes radically. In your design process, in your deliverables, do you do sort of the comparable to an EV-ready situation where you say, if you need more load, to meet more load, here is where wells can come and here is how you can hook them up?
Yeah, I mean, we basically, I agree with that. And I think we haven't run into a scenario where we've had like a big program change. Like it would have to be pretty significant, I would think. Like the first thing is when we do these systems now, it's actually great that a lot of the efficiency of Vermont and like Burlington Electric, we model it and then we go back after occupancy and see how the model did and actually optimize as needed. And then we can kind of predict what could happen, but unless you put like a big server in or something, it's not, there just hasn't been a lot of changes to a building. Like if you're gonna build an addition, then yeah, there's gonna be, well, you're gonna need something else, just as anything, right? So then you'd have to add more boreholes, and if we're designing a project, we would say like, okay, is there any thought about putting an addition in? Or even in our headers, we usually have an option that you can just, it's valved off, you can attach to it, and then you'd have to drill more boreholes, but it's not like you're redoing the whole thing. It's just, and then you can connect to that header and feed your addition. But we try to be flexible. Again, depends on the client, but there's definitely options to like integrate back into that system. And usually, like you find that, again, there might be more capacity in the system anyways. Who knows? Like depending on how the operation works and how the occupancy of the building works. Maybe the building owners optimize stuff even more than what we had thought of. Yeah.
All right, great, thank you, great questions, yes.
Are people going to share slides? I see people taking pictures of slides, and I don't know if they're intending to.
I haven't asked about sharing slides, but we are recording this, and that will be on the Middlebury Energy Committee website eventually, so. Yeah. Anyway.
All right.
Thank you so much.
Yep.
And I also realized I forgot to show the agenda, but you guys already figured that out because the next speaker is Steve Smith. Then we'll have a break and a panel discussion of some people that are users. So, quick pull up Steve's slides. Yeah, I know. All right, this is pretty good. Let's see. I'm not sure why this is not showing in the slideshow rule. Yeah, is this as good as I can do it? Anyway, let me go ahead and introduce the next speaker. So, Steve Smith writes that he... Oh, yeah, sorry. Steve Smith, that's a really big difference, isn't it? He writes that he came to Vermont after graduation to see his sister, liked it, and found a job. And then after his 3-year apprenticeship was over, he passed the licensing exams and started an architectural firm. In 1993, he left and with others started SAS Architects, and he's been there ever since. So their work focuses on complex public buildings with a strong leaning towards sustainability, even in their preservation work. So that's an important piece, especially as we think about retrofitting the older homes in Vermont. Steve's actively involved in projects as a design critic. He also acts as project architect for certain projects, responsible for all aspects of the work from design through construction. Particular interest in sustainable contextual design, and he was the principal in charge for the first 2 LEED Platinum projects in Vermont, the Environmental Studies Center at Middlebury College, and the Forest Center at Marsh Billings Rockefeller National Historic Park. Many of Steve's projects involve the restoration and adaptive reuse of historic buildings, and for 20 years he's worked closely with Shelburne Farms. He's also part of the team that designed Hula, which is the 14-acre tech campus on the Burlington waterfront. I'm sure we're going to hear a lot more about those projects this morning. I was also interested to learn that Steve's firm designed this wonderful addition to the Congregational Church. So, Steve. So, it's right here. Just advance.
The arrows?
Little arrow.
Okay.
Oh, I think you can go.
Yeah.
Yeah.
Okay, cool. All right, thank you. Good morning. I'm going to talk today, I think, about 5 long-term clients and their evolution over the last 30 years about energy. And the slide up there is of the Air Guard base in the Burlington Airport, VTANG. And we've worked there now for 37, 40 years maybe. And it's our work, we've done an energy master plan for it's something I never thought I would get involved with in architecture school, but we've done a series of them, often with George's firm. And they really do the best buildings in Vermont. No one would guess that because they don't publicize it, but they're fully committed to electrification and early adapter of geothermal. And you know, one of the pilots once told me that they get sent over to fight the oil wars. This was back during the Iraq wartime period, and they don't want to contribute to the problem there, which was an interesting perspective. And our first geothermal project, and I think it was actually initiated by the Guard, and it was the fire station on the Air Guard base, and it was in 1994. And at that time, I think there were 10 wells, closed loop system. They insisted on a gas boiler backup. But then in the early 2000s, maybe 15 years later, they expanded the building, and that's what you're seeing here. And they took the gas boiler out because it never came on. And what we typically find here is we initially get pushback from the facilities people. It's new technology, they don't trust it. Everyone likes their gas boilers. And then after living with it for a while, the equipment's inside, it's protected, and really filter changes are the biggest thing. There are some issues with the wells. One of the things I will talk about at the end are problems we've seen over the last 30 years. It's not completely problem-free. So fire station, for that, going to the question about what do you do if a building changes, they added 10,000 square feet, and the change was pretty simple. They expanded the well field, added some equipment in the place where the gas boiler had set, and it's all supported by roof-mounted PV. You know, the whole electrification, you need power, and if you generate it on site, and we also designed a big PV array that powers the base up there too. And then in the renovation, the geothermal also preheats the domestic water. And you know, since that first building, this is another building, the Security Forces building that we did there. And this is 2 buildings actually. It's a district geothermal system that George was talking about. You can have one building heating, another building cooling, or separate parts, very efficient. And we're about to add a 3rd building that may utilize that same well field. And it would have to expand, but, so they've actually are very progressive. But I will say about a month ago, the electrification mandate was repealed. So now we're back on the current projects we're doing there. We're still evaluating electrification, geothermal, and air-to-air heat pumps, but we're also need to go back and look at gas. So, Middlebury College. A lot of these clients are gradual evolution in their thinking. The environmental studies building, it was an old building that was expanded and the envelope was improved. We could not talk them into a geothermal system, a full system. What they did agree to was an 800-foot well that provides cooling for the power, and then the rest, the heating, comes from the steam plant. So it was a LEED Platinum building, and again, it was just the facilities department unfamiliarity with the technology, and it was new to us too. It was actually Wayne George, the founding partner at LN, who was involved in that. But over time, that's other views of the environmental studies. Over time, we continue to work at Middlebury. We've been there maybe 27 years, and this is the president's house. It underwent, again, an old 1800s house, and it underwent a transformation, and the president at the time said he absolutely didn't want to burn fossil fuels, so he was fully committed to doing a closed loop system. It had 10 wells, 225 feet deep. LN designed it, and they converted it from oil. The building was well insulated. A couple other views, you can see the historic part of the building and then the new part. And they added PV on the barn. And then now we're doing Stewart Hall, which is an old, I think 1960, 58 stone dormitory. And, yeah. And you know, that's a full geothermal system, the first for a major building that they've committed to. And they're hoping to utilize the well field and expand it for the adjacent dormitory. So it's been a really gradual change of thinking at Middlebury College. And Stewart, 12 wells at 700 feet. So give you a perspective, and it's 35,000. And again, a big improvement there on the building envelope as part of the project. And then with LN, we did an energy master plan for the Marsh Billings Rockefeller National Historic Park. And it was interesting, all the buildings had different requirements, so we ended up with, it wasn't all geothermal. We ended up with different systems. This was a new building in the background that we designed, the Forest Center. It's a conference center, basically, and they couldn't quite bring themselves to do a full geothermal system there either. So we did an oil-fired or a wood-fired boiler with a borehole for cooling. But as time went by, so this is that little Forest Center, very well insulated, roof-mounted PV. And this is the visitor center, which is from the 1800s. And there, the solution was a geothermal well. And one of the really nice things about it for historic buildings is you don't get any outside equipment. All the equipment's inside. You don't have a chiller tower. You don't have air-to-air heat pumps sitting outside. And it's actually worked out really well. We typically, working with LN, put these systems in. We usually use a commissioning process, which we do actually for any kind of heating system. And they open, and knock on wood, we don't get a lot of pushback. And I always check back a year or two. These are long-term clients, so I see them anyway on the next projects. And the facilities guys really like the systems, very positive. And then this is a project that George mentioned. It's on the Burlington waterfront. It used to be the Blodgett Oven Factory, and there's 3 buildings. 2 have been fully developed, and we have a third one that's right on the water that they haven't gotten to yet. But this photo showed the lakes in the foreground, shows the whole thing, and then that parking lot at the rear is a good thing to keep in mind, because Hula now is, and I think you're working on that, right? Hula now is contemplating converting that 14-acre parking lot into 8-story housing towers. You know, there's a real housing crunch in Burlington. And the beautiful thing about this from a heating point of view is there was I think it was 300-foot or process well. They used, that Blodgett used for process water for their industrial process, but it produced 300 gallons a minute, which is unusually high. And it made the whole use of geothermal. That's just a view of one of the outside buildings. It's a gorgeous site. It's an interior. This used to be their main factory line. And but when we did the calculation, George does all the work on this. When George figured out the cost of the geothermal, I remember the number, it was $250,000 less than a conventional natural gas fired boiler in an outside chiller plant. And the owner, that's the other thing I did want to talk about. It takes a commitment from the owner for these projects. You need an owner, and we find that pretty easy to sell these days. It's pretty rare now. We do mostly big projects, and it's pretty rare that we ever have an owner who doesn't want to use a geothermal system. And payback of 8 to 12 years is what we see with LN and also with other engineers. So, and then they're very durable systems, low maintenance, and you know, they produce no carbon. So I think Hula uses a system where the mechanical room is so simple. There's a big pipe coming in and big pipe going out, some big pumps, and then they just pump the water around. There's localized heat pumps that convert it to hot or cool air, and then it gets injected back in the ground. And so we had to drill 4 injection wells and then add 2 more wells. They each produce 300 gallons per minute, so 900 gallons a minute, and it's 150,000 square feet. So it's really interesting how that worked out. Just another view. I should have included a couple photos of what it used to be. And then Shelburne Farms is a long-term client, and LN and SAS did an energy master plan some years ago. They want to be carbon neutral by the year 2028. And I would say that's a push now, given where we are, but they've been steadily making progress. This is a breeding barn complex, is what they call it, and there's a couple buildings in this photo that have been converted to geothermal. We've also used air-to-air heat technology out there, and then they do have some pellet boilers. This is a coach barn. They're converting it. It's built in 1902. It was finished. It took a few years to build. But under construction now. LN designed the system. It's a geothermal system. And this is a kind of a model we did to show, but they're going to have education facilities, conference facilities. There's a big courtyard in the center. And there, it's a National Historic Landmark, not just a National Historic Register. It's the only, Shelburne Farms is the only National Historic Landmark in the state. And so the project got quite a bit of scrutiny, both from MPS and the local DHP, Division of Historic Preservation. So only part of the building will be heated and cooled. And there was no way in these main spaces that are in the front of this plan, they've got these beautiful beadboard walls. I don't know if these spaces. You can see that you just can't strip the beadboard off and insulate behind it, and it was masonry on the outside. So all we did here was add storm windows, low-profile aluminum storms, and above the spaces to be heated and cooled, there's an insulated cap at the roof, and you have to insulate a building like this is a whole process, because you don't want to do harm by insulating, so you have to select the right system. So I think this is due to be done. Oh, the other really important thing is, obviously you can't run, or we didn't want it. This shows it the way it was. These lights have all gone away, but integrating the mechanical systems into this project, everything's located up in the loft, and the only intervention you see are black grills in the ceilings, so you get hot and cool air introduced. The lighting's been changed, but the integration is really important. And the other thing we couldn't, and this is both Hula and the Coach Barn have a commercial kitchen, and at Hula they decided the technology didn't exist, so that's the only gas used, is a makeup air unit for all the air that the hood sends up and outside, a huge waste of energy. This project, talking about developing technology, George found a recirculating hood. So over the big commercial equipment, there's a hood that, and if I veer off from the truth, let me know. So the hood takes the air and recirculates it and puts it back in the space, and at the same time, and then hot water, domestic hot water, is also made from the warm air in the kitchen. So there's no makeup air unit. The heat's not vented out. In a historic building like this, that's difficult to do anyway without changing the appearance. Probably couldn't have gotten approval. So it was another really good example of technology getting to the point now, and this is very new. Like this, I mean, last couple, at least very new to us. We hadn't done it.
Yeah, the thing is to know that there is ventilation air. The idea is that you use energy recovery now because it's not grease exhaust. So you basically filter the grease exhaust and put it back in, and then we have a separate ventilator that can ventilate the space, but you don't need it, because it's ERV and they're efficient, you don't actually need to add a bunch of heat with the ERV. So that's kind of it's not like we're just leaving unventilated. There is ventilation, it's just now able to have recovery. And there are other systems that in the past they tried to do that, but it seems like this is the one that's kind of the standard now. Going into this, there's a couple other products like it. So.
The other thing that's really interesting is the changing political climate. When we designed ECHO 20 years ago, we explored the idea of using lake water as the heat source and it makes a huge amount of sense. Like Cornell University has, I think, an 8-foot diameter pipe, and they cool their entire campus, which is enormous, with water from Lake Cayuga, and then they put it back. We got approval from the feds, believe it or not, for ECHO, but the state would not approve it. Even though we calculated the thermal increase of Lake Champlain, and it was, I think, 14 zeros, they wouldn't approve it. But we went back to them at Shelburne Farms. It turns out the original owners put a 12 or 14 inch diameter pipe a couple hundred feet out into the lake for their water source, and it still has a little bronze top. It's all in perfect case. Well, when we talked to the state about using the geothermal, they said, yes, we're open to that now. So there's been a shift, and the use of lake water for heating, cooling, I think is everything's there. And the state in concept hasn't been approved, but approved taking this water, using it, running through heat pumps, and then putting it back. So there are some changes coming. And then the last thing I wanted to talk about or show you is I live in a really modest, and I've been there 45 years now, 1787 Vermont farmhouse. And when we moved in, it was no heat or power on the second floor, and it had a big oil furnace down in the basement and no insulation, completely frigid upstairs. And over time, we changed to a gas boiler. We then, we used wood heat all the time. So there's been it went to oil to gas and now to geothermal. About 2 years ago, George designed a geothermal system. And I had a well, I've got a good well, 45, maybe even 60 gallons per minute. So I had enough to use an open loop system. And it would have been water from the well, which is right next to the house, through a heat pump. And I have a pond back there and put it in the pond or do an injection well. And I used the same well driller that came years ago and drilled the well, Claude Chevalier, and he talked me out of the open loop system here because, one, I have really hard water. So he said that over time, that's going to gum the equipment up. And then the second thing is he knew of someone who had done this, and they actually drew the water down, so they ended up no heat and no water. So I drilled, Claude came in for $30,000. He drilled 2 wells. I think they're 200 feet deep. He ran all the piping, did all the testing, and they'd simply run in through the old stone wall into the basement. And it's a little more complicated than it would because I didn't want to run ductwork around the house. It just would have, there's no way to do it. So I've got minimal duct. First floor is cooled, second floor only 1 bedroom. And if it had been just me, I just would have done the heating. So I have 2 pieces of equipment down there. So the cost was maybe 20% higher. But it's actually worked out really well. And one of the questions I saw was, what are the financial things? There currently is an Inflation Reduction Act. We haven't talked about that. I don't know, it's been around now 5-6 years. But yeah.
In the ITC, which is what it really is, it was a upgrade to that. So the ITC has been around for, I don't know, a very long time. That was before the 30% credit. It went down to 26, and then this Inflation Reduction Act happened, and it actually expanded geothermal for tax exempt entities, and commercial was 10%, now that's 30%. I think it's still around now, but we're not sure where it's going necessarily. But it was this is where geothermal kind of had a resurgence, I think, around here, was that IRA.
Yeah, so the cost of the system with the 2 new wells, everything done for the house, was about $100,000, a lot of money. The IRA or the federal government paid 30% of that, so $30,000 or $33,000. And then Efficiency Vermont paid $2,500 a ton, so that was around 18. So the cost was $52,000. So still more than air-to-air system, but I think over time, it's gonna be a lot less expensive. One of my kids put an air-to-air system in his house, and it was about $30,000. And the Shelburne Farms has done one that was $60,000, a ducted system. So, you know, it was expensive, but something I felt like I really think a lot about the carbon issue. It does all these projects that involve electrification often require new service. The Coach Barn did. Pretty much, if you retrofit a building, even my house the service was barely adequate. But it was designed, the system was designed, I just finished this barn. It's actually I'm still working on it. That's where I was this morning. But it was so easy because George had sized the equipment. I ran 2 pipes out. There's a heat pump there at the far end there. There's an apartment and a little wood shop. And it was a simple thing, cost about $15,000 to add this to the geothermal system. So the idea of a district system really makes sense. And then last thing, I also want to share experience, the kind of problems that we've seen, which surprisingly, I don't know, maybe we've done 20 decent-sized geothermal projects. You've done a lot more, but we tend to hear about the problems. So we had a project at one of the air guard projects where one of the wells collapsed. They got down into the rock was unstable, it collapsed. They had to offset, re-drill, so there was a cost. It didn't deter anybody, but there was an additional cost there for the owner. We had another project at the Green Mountain Power headquarters down in Rutland, which is quite a big project. And they were fully committed to doing a geothermal project, but we drilled there, and it was at the base of a hill, and the artesianal pressure was outrageous. It blew the casing out of the ground, and the well driller essentially said, I can't put a well in here, and then you guys did the calculations, and the electricity it would have required to put the water back in the ground was too high. So they went to a more conventional system, and that's a rare problem, but it's worth mentioning. The worst problem we saw, and LN was not the engineer, that our mistake, was a big building for the Army Guard at the Jericho Readiness Center. And they had a tight site. It was a 3-story building. The wells went underneath the parking lot, which is perfectly fine. But they didn't put the lateral lines in deep enough, and they didn't insulate them. So what happened is when they cleared the parking lot, frost drove down, it turned the liquid, the glycol, into like a slushy. And to resolve that, in the middle of winter now, they had to add a gas boiler, and they supplement. So easily fixed. Well, the lines could have been deeper in insulation, but it was a mistake that was made. Luckily, they had a sense of humor about it, and they still use geothermal for everything. And then the other thing, that we just finished the state police headquarters, or field station, I guess they call it, in Williston. And the owner elected it's fully geothermal, but they elected not to do a test well. And so because of that, as they got into the well drilling, they had, again, underground problems that weren't expected. And we had, I think, double up the number of wells, and they were all shallower. So there was a cost there to do that. And you can't always avoid those problems, but a test well is a good idea. And they cost maybe $20,000, and you do the conductivity testing to see how the soils react. So that's my experience. And even products, I'm getting old enough now, even projects like Echo that didn't do geothermal then are now, their original equipment is aging out, and they are putting, I think you guys are designing, they are doing a geothermal
Yeah, we
system.
drilled a well, so
Yeah.
they're ready to go.
Yeah.
And the nice thing about, again, just to put on it, conventional systems, like this building has a water source heat pump system. This building could be converted to geothermal if desired. There's a few things that need to happen, but it's possible to do that. So there's, even if you have a conventional heat pump system like Echo does, there's ways to make that work. So that's kind of a neat, it's just very flexible technology, which is kind of cool. And it's not like even if 15 years ago there's something that was done that you regret. It's always, there's a way to integrate it usually.
Mhm.
All right, thanks. Thanks, Steve. I'm sure there are questions. Yeah, Susan.
On test wells, can you use the test well in the project?
Yes. Yeah, absolutely.
Almost all.
Yeah, you drill it to the depth you want, and then that becomes well number one. Yeah.
Amy.
You mentioned costs associated with the well at your house was roughly $30,000. So my
Mhm.
question was.
Two wells.
Two wells. So you got 2 wells for 30.
2 wells, 200 feet.
Okay.
Yeah.
My question was, is the cost of drilling these wells for this purpose comparable to drilling a well for domestic water
Yeah.
purposes?
It's exactly the same
Okay.
process. And I will say, well drilling can be pretty disruptive. And we've learned, like at the Shelburne Farm projects where we've done it, first step is dig a pit, because everything they're drilling out of the ground has to go somewhere. And there's usually a lot of water and all the grit, that limestone typically in Vermont. So the best thing to do is a pit and dump it in there, and then you have some cleanup to do. So,
But they don't have to get water, so that's a nice.
no, you don't need water at all.
That's a nice.
Yeah.
Yeah, yes.
Thanks for your talk, really inspiring. I spend some time in these public buildings, and it seems an odd aspect of the poly crisis that a lot of these public spaces are empty or very thinly populated much of the time. There are probably fewer people at Hula right now than there are in this room. Thankful as I am that Russ keeps it open for the public. My question is, to what extent do your clients or prospective clients, be they retrofit or new build clients, prioritize the value of passive heating and cooling so that we don't always have to keep the switch on?
Well, when I came here, I ended up, my first job was for a little firm in Heinsberg, and that was their specialty. I was, I think, their first employee, and was passive heating and cooling. And after 3 years of hard work and failed attempt, I concluded that Vermont's not the place for passive heating and cooling. There are places in the world for it, but it really, we tried everything, trom walls, water tubes, went through the whole gamut, and they always had issues. It never, the quote, energy modeling that the two partners did, it wasn't factual. And the promises they made to the owners never panned out. So I got away from all that for maybe 10 or 15 years, and then got back into it when these different technologies came up.
Thank you.
And your experience with Hula is, so one building is empty. The tenants, I'm not empty, there's a couple tenants in there, but after COVID, they've never come back. They still pay rent, but it feels like a ghost town. The big building, every time I'm there, is really active. So, and certainly some of the government buildings, the same thing. Some people want to work at home, and they can be underpopulated at times. But carbon, so a couple things that motivate people to do geothermal. Carbon's a big deal for some people now. Some people deny it, but a lot of people in Vermont particularly really are trying to reduce their carbon footprint. And the other thing is just economics. Over time, it's less expensive. Yeah.
Is there anything that you, or maybe also George, would like to see happen in the state of Vermont that would allow you to do more, for us all to do more with this technology? Is it workforce, is it incentives, is there anything that would make this easier for all of us?
It's become very expensive, and that's due to, I mean, that's due to there's not enough mechanical subcontractors who around, and they're just, the demand exceeds, what they can do, and they've all, how much has it mechanical costs increased over the last 5 years? Just doubled?
Please.
Yeah. So that's a huge thing. That's a, but that applies to every kind of system. It's not just geothermal. It applies to all of it. The initial capital cost, like if the federal contribution goes away, that'll be a blow, because it'll extend the payback out, and not everyone is willing to take on technology with a 12-year payback. So.
I can answer your question of what I'd like to see. So yeah, I mean, I think we're in a time right now where I see that, at least for me, I have 10 years to make this technology viable without incentives, right? Because 10 years they could go away or reduce. So I'm working with a handful of well drillers, mechanical contractors, to try to get these systems installed, learn how to make these less expensive to install. And I think there's two things that I would like to see. Is one, and we were just talking about this earlier, is a bridge loan, so that the owner doesn't have to pay the extra cost up front through the construction process. And when they get the incentive just goes to a bank, a green bank, or whatever that is. So that so when we're trying to have an owner who's like, okay, there's this system and then there's geothermal, they're like, well, that's 20, 30% more. I can't. I gotta finance that. Well, no. Now there is a bank or someone who can finance that, maybe do all the paperwork so that they don't even have to worry about it, and streamline that process, and then they just take the incentives personally, and then the cost of the project is like no other, it's similar to any other mechanical, or maybe even less. That would be, I think, a huge deal. That would be an easy sell for owners, I think. I think that's a hard one to get over. And two, it was what I was talking about with residential side. Again, we're not a big residential designer, but that disconnect between residential and well drillers, if there was an incentive that could be given to the contractors, residential contractors, builders, to put in geothermal, that may assist more residential work, where they might have an incentive to say, okay, let's just not put in this air source system or furnace or whatever. Let's think about this, and I get an extra whatever it is, and maybe that could promote that discussion, and maybe the well driller gets something too. But that's that disconnect. And I think once everyone sees that and does it, it's actually, I think, it's easier to install, honestly. It's all hydraulic piping, there's no high pressure refrigerant lines and all that stuff. So I think there's, the bridge one I think is the big one, and that could go for residential and commercial. I feel like that's a big hurdle that I've been coming into. That's great, I like these incentives, but I still have to pay the upfront costs, until through the construction. I think that's a tough one, tough boat to swallow for sure, when it's, you're having to do so.
Wondering about the drilled wells. What do you use for casing in these drilled wells, and how long does that last?
Yeah, so it's steel casing, and interestingly enough, and this is one of the things I've been trying to figure out how to do, which I am getting there, I think, but it's still difficult, is that the casing in closed loop is really only needed to allow so the well doesn't collapse. Once you grout it and put the piping in, there is no need for the casing. It's not like a normal water well where you need, it's there and you want to make sure it doesn't collapse. Once it's grouted, it's not going anywhere. So that's another thing when we do test wells. It's always like, okay, how much casing do we need? Which casing is basically, there's an overburden, which is how much soil and stuff is there before you hit bedrock. Because once you hit bedrock, you don't need casing, it's not going to collapse typically. So that's a good reason for that is that it's an expense, right? That $30 a foot or whatever that is for casing adds up if you have a bunch of overburden. So there's different methods of drilling. This is me talking to well drillers, how you drill with fluid or how you have air hammer. And there are scenarios where I think you could go into overburden without any casing and make it work. But that's one hurdle that it seems, I don't like waste, and that just seems like a waste to me. I know it's the process that needs to happen, but like, if that casing could be removed, which we have been able to do that in some instances, you wouldn't need it for close loop. So like, again, that's $30, $35 a foot that could be eliminated from geothermal drilling if we could figure out a way to do that. So.
The casing's heavy gauge steel that lasts a long time. I don't know I'm sure soil conditions vary. But what you're saying is, even if it rusted away, it wouldn't affect the system.
Yes.
It seems like the well drilling is a major cost. Maybe you went over this, but what are some of the requirements that you look for in a well in order for it to work for geothermal? I mean, are you looking for temperature, water amount? What exactly are you looking for?
So you're not really looking for water. If you find it, it's a bonus, because then you can go to a less expensive open loop system. I mean, and you need a decent amount of water, but if you find, like Kula, you had so much water, you've got to re-inject it in the ground, but even with the injection wells, it's less expensive.
Yeah, there's also some scenarios where we have closed loop, but you hit a fracture and you try to grout it and the grout just gets washed away. In those cases, you know, well drillers are pretty good at understanding like, where is that in the system, and you put like pea stone in instead of the grout. So like you might have a scenario where you grout it, the piping goes through it, and then there's this pea stone, which really means you have this water that's flushing through this basically HDD pipe, and then you grout it back up to the surface, and those actually have really good conductivity because you actually have this big water flow that's exchanging that energy with the ground. That's kind of the bonus. So when we like see wet soils or wet drill lines, we're like, okay, there's probably good conductivity here. But in general, yeah, the well water here is typically at 50 degrees everywhere in this area. Obviously, when you go south, it actually gets higher temperature. But it's mostly understanding how much casing would be required as far as what the depths of the wells are going to be, and geology. Like there's certain dry sand and stuff that aren't as conductive. But that's why we do a connectivity test, or if we have the profile when they do a test well, they give you the profile of like what each thing is, and you can kind of get a good idea of where your connectivity is going to be, and that translates to how many boreholes you're going to require.
I don't understand the well with no water idea. What is that?
Well, so that's a closed loop. So that's basically where you have a pipe that just runs water. The pipe itself has water in it, and it's closed loop. It runs through this pipe down into the ground and then back to your building. That is just transferring energy with the ground. So it's a surface area calculation versus a flow water calculation. So you're literally, if you have say 80-degree temperature going down because you're in a cooling mode, that 80 degrees goes down that borehole and up, and as it goes down and up, it exchanges energy with the earth, and then when it comes back, it's say 60 degrees.
Where does the water come from that gets heated up and added to the loop?
There's no outside water. It's all the water that just gets pumped, like a boiler system in your house. It gets pumped through your building. This just gets pumped also down into the.
But it comes from the earth.
No. It's just like imagine having a big heat exchanger that just exchanges with the earth. It's all closed. There's no water touching this process. It would be like having a big heat exchanger outside, and you're pumping water through this heat exchanger. It's not outside. It's not getting exposed to the elements, but the hot air or cold air is allowing for you to change the temperature of that water that's being pumped through that heat exchanger in that closed process.
It's about the diameter of a garden hose. So think of a garden hose going down 200 feet and back, and then it connects to a pump in the house, and it's just pumping a liquid through that hose. And the other thing, they typically, so it's in a 6-inch diameter hole, these two garden hoses going down. They typically add a grout there, so the grout will facilitate the thermal transfer, because if it was just sitting in air, and you don't need the grout if you have a well full of water, because water transfers the heat really well.
Yeah, it's kind of like, think about like a solar pool heater or something, where you're running water through this closed process, but the sun is hitting that and allowing you to heat that water that is getting pumped through the pool, something like that. Except that sun is really the ground, if that makes sense, and this water is just getting flowing through that and exchanging that 50-degree constant ground temperature.
So the water supply that the building develops supplies the water to the.
Yep.
It's actually a water glycol solution. So it was interesting when on my house, when it started, there's a glycol feeder when glycol doesn't freeze, but it's sitting there, and every once in a while it would burp. It would let this really loud noise that you hear through the whole house, and it was adding glycol and getting the air pockets out of the line. And then it just stopped. So if you have a leak or anything, that feeder just automatically puts the glycol in. And the glycol is, I mean, obviously it's
Twizzlers.
Yeah, it's a glycol water solution, and it won't freeze. A guy assured me if you lose heat in your barn, don't worry about the piping freezing, because it won't.
But it's food grade too. It's not like a toxic
Yeah.
glycol system. You can use it in food products actually.
Yeah.
Oh, for me?
Yeah.
I'm sorry. Okay, well, you talk about cooling, let's talk about heating. Let's say you need 160 degrees coming out of that well if you're gonna heat your house for the winter, which is approximately the heat that you're gonna need off of.
Actually, you don't need 160 degree water. My house heats with about 120.
Okay.
And it's fine.
But doesn't it cool off? You don't lose any.
No, it's just like it did before. I mean, it won't work with conventional baseboard radiation, and you could explain why, but I've got the Runtal radiation flat. It's like the old, it's more European, and it works flat plate, I think. It works great. Yeah, so 120 is what you get. Radiant heat in the floor works great.
So how deep approximately would you go?
No, yeah, so it's not, the well itself isn't producing the 120 degree water, or 140 degree water. It's, the well connects to water-to-water heat pump. So the water-to-water heat pump takes that 50, 40 degree water and heats it up to 120, 140 degrees. So there is, it's like, that's like the energy transfer I was talking about earlier. You're using, through a refrigeration process, taking that 50 degree water, heating it up to that 120, 140 degree, and that's how you heat and cool. So you're not, it's not like you're directly using the geothermal to heat or cool. There is a piece of equipment in between. It's just more efficient than a boiler, for example, where you, like again, are generating something, energy from a fossil fuel or electric resistance because of that energy transfer. So that's where I was saying things are more efficient when you don't have to have, when you go to 50 degrees to 100 degrees or 120, that's a lot more efficient to do than 180. You know, even if the technology's out there, that's more energy to do so. But in some instances, you have to run at a higher temperature if you don't want to place all your terminal equipment, which may be sized for a higher temperature.
But you still need supplemental energy in order to bring that temperature from 50 degrees up to 120.
Yeah, so that's that heat pump.
Yeah, so the only difference is trying to bring it, so if you're recycling the water through your radiant heating floor, then, you know, we're bringing water in at, 80 degrees and heating it back up to 120. So it's,
Yeah, it's just a different, I guess I'm not quite getting what you're saying, but basically the process is not, there's this one process, the geothermal side, that is running between 30 and 80, 90 degrees, say, based on heat or cooling. That loop goes up and down. The other side is the process, depending on your system, it could be an air-based system where that's running between 30 and 90 degrees, and you're heating or cooling from that. If you're talking about what Steve's house has, is you're actually creating hot water. There's a piece of equipment that uses that in heating mode, it would drop, the temperature would drop because you're absorbing heat from that loop. And then you're using that 40 degree water to heat to 120 degree water. So it's just like, that's your boiler basically, essentially. So instead of a boiler, you're using this water-to-water heat pump to meet that heat requirement. But it's more efficient because you're not generating from a carbon base. So you are actually exchanging that energy. So that's where you get that efficiency in there. But yeah, you still need electricity to make that process work.
Kristin, you had a question?
Steve, I was just curious, I'm going to talk later about my workplace, but we've wanted to upgrade our home to not using I was wondering if you could describe the cooling system you put in your house as a retrofit, if you're using water and trying to chill the water, but you don't have the infrastructure in place in your home for cooling, how to get away from the window unit air
So
conditioners.
the cooling is an air system, so it's a water to air produces
Okay.
cool air. So you gotta run some ductworks.
Okay, you did do that.
First
Okay.
floor was easy because I have a basement. The original house had a basement. I just ran flat ductwork around. It's an old house, so low headroom, but it all worked, and floor grills.
Yeah,
Second floor was a challenge.
yes.
So just getting the duct vertically through the house, and I
Yeah.
only did one because of that.
Yeah,
So there's one bedroom
yeah,
that stays cool.
that's what we were thinking. as
Yeah,
well.
yeah.
Okay, thank you.
All right, let's wrap it up here for the questions, although Steve and George will be around, I'm sure, at the coffee break. But can we thank them again?
Thanks for being here. And it was a big project, so I'll try to move somewhat quickly so we have time for everybody. Many of you, do you all know where we're located? If you drive up Route 7, you'll see on the left-hand side, as you're heading out of town, a big, it was a grassy kind of lawn, and then it turned into a big pile of rock and dirt. So those are our borehole sites, which are getting fixed up now. But our center is on Exchange Street near RK Miles, and we serve about 100 people a day. It's like a school for older people who need support of nursing, social work, etc. So that's, I'm not really in the business of infrastructure improvement, or I know very little about technology, but I've learned a lot in the past year. And our project, I have to say, was funded in large part by the Home and Community-Based Services. It was a grant opportunity that was ultimately funded by the American Rescue Act Plan of 2021, so we couldn't have done it without that money. Here's what we looked like before, a beautiful campus, as you can see, kind of a home away from home. And my goals in this project were to improve the comfort for the older people at our center. The building is 20 years old, and it was surprisingly not, there were cold corners, there were hot corners, and people were either wearing blankets or feeling too hot. And so we were trying to manage some of the comfort, and also after we had a pandemic-related closure for 15 months, when we reopened, the first day we opened, the chiller failed, and I was like, oh no. How long does a chiller last? And guess what? It lasts about 20 years. And so I thought, oh, my time is limited. What do I want to do next? And I certainly don't want to put in the same thing for the next 20 years. So that really sparked my thinking in 2021. And we also had to keep things running, so we were kind of in this project building the plane while flying it, which was a little bit of a challenge. And as I said, or as I wrote in my bio, I really care about energy efficiency, wanting to reduce our costs and our carbon footprint. So what did we do? We had to, I think George spoke really well to this point, we had to evaluate our energy usage and building efficiency using thermal imaging and blower door tests. So you don't just say, I want to do a geothermal system. You have to say, what's our energy usage and how can we be more efficient? And then we used LN to do an energy modeling to see what's going to be the best bet for us in the long haul. It turned out that the geothermal heat pumps were the best for us. And we set goals for our efficiency upgrades. They were stringent goals with Efficiency Vermont, and then LN designed the ground source heat pump system. So we had three aspects to the project. One was just reducing the leakage in our thermal envelope. It was very leaky. I'll show you that in a minute. We ended up replacing windows, replacing the siding, and adding insulation, and we had to insulate the roof deck because a lot of energy was being lost through the roof. We replaced the chiller and the propane boilers with ground source heat pumps. That meant the water furnaces. We added a domestic hot water heat pump, and we did use a backup high efficiency propane boiler. We actually had to in order to kind of keep the center running as they were installing the heat pumps. And we added solar panels because I wanted to make this an affordable project for the future. So that kind of takes the edge off of the increased electric usage. And we added a pavilion for our outdoor activities that gave us even more roof surface. So you can see that when we first did our blower door test, we had a really significant air leakage going out the building. And if you look at the examples, you can see that we're losing a lot compared to what was considered leaky is 0.6. We were at, in the worst case scenario, 2, and at the better case scenario, 1. And then you can see that a tight building is 0.1. So we had a lot of low-hanging fruit to improve our situation. So our first project was how do we insulate and how do we do a better job? And given the way the roof was constructed, we had to insulate the roof, which is a little bit unusual. So there's some technical, we went from a vented roof with fiberglass that was basically kind of falling down and changed to an unvented roof with 8 inches of polyiso foam. So we really got an airtight roof in place. We had to do a lot of taping of the seams. I just want to say that there had to be a lot of intelligence applied to this problem. It's not just you go find some people off the street to put a roof on. You've got to really think about what you're doing and not create more problems. So we were lucky to have a GC who was really committed to doing a great job, and it was time consuming, but he did it. And you can see here, the roof wrap is the white stuff, and then the polyiso is gray, and then there's that additional plywood top that they're going to add the standing seam roof to. So there was 8 inches of insulation between the polyiso and that, the wooden part of that had foam underneath as well. We uncovered some rot, which was predictable but disappointing, so we were able to fix a lot of the problems. And just did a lot of taping. The original construction wasn't very inspiring to see. So just with the roof deck insulation, you can see that our progress, we went from here to here, just by taking care of that roof. And then we had a final test that with the having done the sides, and so we got improved tightness. That allowed us to size a geothermal system that was not huge. So we went to, we had to have a system where we could use 10 boreholes instead of more. So that's our front lawn there, Route 7 is over here. And that's the drilling rig. So this is the space where we put in the wells. And then we ran the pipes under the driveway to the building. The building's kind of like over here. This was our old system with the boilers. There was some demolition that needed to happen. The fan coil units had to be sized larger because we were using that. Remember, George was talking about like having 180 degrees going down to a cooler temperature of 120. You need to have bigger fan coil. We decided not to replace all the piping in the building. So we had to size up the fan coil units, and that required some infrastructure changes for these bigger units. You can walk away from this just saying, oh, it can be more complicated than you think it's going to be. But we had to get structural engineers, making sure that we were able to support the roof deck and change some internal things. We had to have more space, actually. I hadn't anticipated that, but we had that one room that you saw before, and now that room had a lot of piping in it and some buffer tanks. These are the actual water furnaces. So the one in the front, that heats the water. That one cools the water. The middle one is the backup in case either the one that heats or the one that cools fails. And this is some of the piping that we had installed to exchange heat with the water in the building system. These are some buffer tanks. So this was the room that had all of our equipment in it before, and now we had to find another room to put the equipment in. So fortunately that worked. Something that allows us to be very efficient is you have to have a control system. So we're controlling all this from a computer interface. I'm not going down there and turning anything on or off with those switches, but if a room is too hot or too cold and I want to change the settings, I can just do it through our online control system. And then part 3 was just adding solar panels on. So we worked with Bristol Electronics to add 193 panels. That building was new. We used to have a tent, which you saw in the first picture, and that was as a result of coming back after the pandemic and wanting to be outside more, and we thought, hey, this is great. Let's get a permanent structure, and that allowed us to have more roof surface. And then we also, not in this picture, have a van shed that has panels on it. So our energy usage has really, we've generated more power than we thought we could with solar panels, and our electric bill is about half of what it was. So from $3,000 a month to $1,500 a month or less. Our propane, we do have that backup propane heat, which I don't think we'll use that much, but we had to have it installed anyway, and then we have a domestic hot water heat pump, so even our hot water is on our electric system. But we use propane for our kitchen because I couldn't find a good alternative for a commercial kitchen that used, you just need a real workhorse of a stove, and I just couldn't find anything I liked. So we went down to about 54 gallons of propane a month, which is about $150 a month from like a $1,500 a month propane bill. So huge energy savings right off the bat, which is really gratifying to see. I guess the other thing I want to say is part of the reason we were also able to enroll with Green Mountain Power in a flexible load management plan. So they're incentivizing our efficiency, and if there's a peak event in the community and they, like everyone goes home on a really hot day and they flip on their air conditioners, that's gonna suck a lot of power from the grid into people's homes. If we say we can pre-cool our environment and we don't need to draw that extra electricity, they say, okay, we'll control you through that system I showed you before. They can come in and kick our cooling on early through this computer system so that when everyone else is needing power, we aren't needing power. And so we're able to be part of this incentivized program, and that's helped cut our electric bills in half. But also we're generating a lot of solar energy, and we're getting some credit for that. So people want to know how much it cost. So it cost about $750,000 to tighten the building envelope. It was a 1.8 almost million for the geothermal. The solar was about 450,000. These numbers were just kind of I threw them up there. So we spent, there's still more to do too. We still have some finish up work to do. So I would say it's more like a $3.25 million project. And we received 1.795 million or 1.8 million from that grant through Home and Community-Based Services. We got about 83,000 from incentives. That's Efficiency Vermont, Green Mountain Power, a couple other smaller incentives like that. And amazing support from the community, $790,000 fundraising. So that was really incredible, and we're hoping for the $400,000 back from the Inflation Reduction Act. And we're having to hire someone to help us figure that out. So that was also, I gotta pay you guys $45,000 to help us get $400,000, but it's too technical, I can't do it. So I think we're gonna end up spending about $200,000 for this, which is pretty amazing, actually. Because we would have spent, I don't know, at least that much money on getting a new chiller. right? And then we would still be expending all that extra expense on energy. So I feel like huge win for us and for the community that we serve, because this is really what we're about. Our goal was to keep us really running well for the next 20 years, and I feel like we're there. So that's our project. Thank you.
Let's hold questions for the panel until after the three people have spoken. That's okay. Just down. Okay, so our next speaker is Huston. He's the Vice President of Preconstruction at ReArch Construction, where he leads the planning and development of commercial construction projects with a focus on collaboration, innovation, and sustainable building practices. Got 35 years of industry experience as a licensed architect, and he's the primary client contact during the pre-construction phase. In fact, I first heard him speak at a select board meeting. Very impressive, I have to say, the way you handled that. Before joining ReArch, Chris held leadership roles at Danisco Design in Boston, Breadloaf Corporation, and his own firm, Bellwether Architects. And he has a wide range of experience in designing and constructing award-winning buildings. He's a graduate of Roger Williams University, a longtime Vermont resident, where he enjoys outdoor sports with his wife and 3 children, furniture making, maple sugaring, and creating art, natural world. So, Chris.
Super, thank you, Alice. Appreciate that. Actually, I really enjoy, Kristin, that was inspiring. I think many of these projects that you've already heard and that you'll hear in the last 2 panel discussions are really, I'll say it's a force of nature, if you will. Like, you really have to be determined in terms of making, Kristin could have taken the easy approach, replace, one piece of equipment and not done all that other work to get to an incredible result. So, and I'll touch on primarily on the Ilsley Library, the focus right here, but I'll just also speak about a few other projects as well, and with a focus on what we've learned. So that's really the intent. As Alice mentioned, I've long been really inspired by projects that are, I've really spent my career focusing on sustainability. In my role right now as pre-construction vice president, I'm not designing the buildings, I'm working with the architects and engineers for the construction manager side to make sure that we're listening to the client, we're achieving the goals that they've set forth, and really focusing our energies to make sure that we've taken every opportunity to reduce carbon, make our buildings as sustainable and as energy efficient as possible. And I'll use a few very specific examples as we go through. This image right here is actually the new OnLogic headquarters. It's in South Burlington, right at the Whale's Tails, and that's their engine of the boiler room. I won't go into any detail because that's a whole talk on its own on that system, but exciting geothermal system. So as I mentioned, that top building right there, OnLogic recently completed, but a wide range of commercial buildings. Like, we done one large, this deck house is a private residence, but it's in all purpose, in all effects, it's like a commercial building. It's large and very automated and so on. Kimball Union, that's a dorm project. So again, it's touching people, it's making thermal comfort. It's also, those projects that we can all be really, really proud of for many years to come. So I'll really focus a little more detail on Ilsley since we're right here. Alice Hallway, George mentioned earlier, that's an affordable housing project. So if we can make it work for an affordable housing project where the costs are so tight, but it's exciting that the Inflation Reduction Act has really made it possible. We have several Reed Commons and other housing projects. So in the Winooski School that George, we do an awful lot of work with George and his team. So focusing on lessons learned. So this is Ilsley Library to be, coming out of the ground here. Frankly, we're pouring concrete on Monday on the Main Street side of the building. If you've been watching it sort of get, demolishing the two editions, the 70s edition and the 88 edition, we're going to start to come up out of the ground. Now, one of the first things that we did was drill the geothermal wells. In doing that, backing up, this was a design competition that the town of Middlebury put out to local and regional architects and engineers and construction managers. One of the overarching criteria that they put out in their RFP was that it be as environmentally friendly and energy efficient as possible, while at the same time being welcoming and thermally comfortable and controllable and all that. To us, a geothermal system was an absolute no-brainer if the site would allow it. And really, I say if, we're really going to focus on an open loop system. These are almost all open loop systems, so that's been our primary experience. So that I'll really be focused on that technology and those lessons learned. Starting in the very beginning, as you saw with George's presentation and Steve's, having the right architect, having the right engineers in place at the very beginning, and whenever possible, we always, as a construction manager, really like to be at the table from the very, very beginning of the planning process. So we can, frankly, provide cost information, schedule implications, logistics planning. That's really my role, is to try to help our teams come together as a unified front. Specifically, though, in looking at geothermal, having the right mechanical engineer, a hydrogeologist, especially with an open loop system, is really very valuable. And I'll show you some diagrams that Steve Revell at Lincoln Applied Geology created for us, and we work with him very often. And really, really important is the drilling crew. Spafford's was the crew that worked on Ilsley, as well as Elderly Services. And ultimately, I'll touch on this relative to it's a science experiment, and that's the truth. You don't know what you're going to get when you start drilling. So having that experienced team, as Jeff Williams from Spafford is drilling, and he's on the phone with either George Nelson or Steve Revell to say, this is what I'm finding. Should I keep drilling or should I stop? Do you want to come out and check things out? It's that kind of communication that's really, 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 we found it to be really critical. And that experience, that second bullet there, is relative to the flow that you need. Again, do we keep drilling? At Ilsley, the first well that we drilled, call it the test well. I think, Susan, you asked, is that a test well or not? Yes, it's a test well, but as Steve said, it becomes your permanent well. Ideally, if you hit the water and it's the right depth, then everything's working. At a couple 100 feet on the first well, we hit a big void, and Jeff Williams calls me and says, "Hey, Chris, we've hit this big void." I'm like, "Okay," I'm picturing an underground cave or something, okay, what does that mean, Jeff? Well, I talked to Steve Revell. We're going to fill it with cement and keep drilling. I'm like, "Oh, wow, that's interesting." Well, tell me more about that. So ultimately, for the production well, what you need is really clean water. The turbidity of water for the production well can really muck up your pumps and your heat exchanger. We heard about, Steve had said about hard water. Well, this is the same situation. So ultimately, that at a few 100 feet, there was a lot of fractures, a lot of sand, a lot of gravel and clay. So really wouldn't, even the flow was good, but the water quality required us to keep drilling. So he filled it with cement to allow us to keep sort of penetrating down through that layer. And that first well ended up, I want to say it was We do also have Judith Harris here, our owner's representative, clerk of the works, and again, going to the point of having the right team in place, allowing everybody to be on the same page is really, really critical. So that first, the production well was 585 feet. We hit 100 gallons per minute on that first one. So what was interesting, actually I'll get into that in just a second when I get to the maps. I'll keep going through the lessons learned here. The other thing that Steve Ravel, we found out on the OnLogic project, Steve tells us precisely where to drill. Well, we had some encumbrances and we had to move the well 40 feet. When we did that, the yield went from, say it was 100 gallons per minute expected and went down to about 30. So he's like, do not move the well location. And so that is really, really important, and having those accurate feasibility studies before you drill anything is really, really important. So that was another lesson learned. You've heard a lot about the Inflation Reduction Act. For ILSI, we are leveraging over $500,000 on the entire system. So that's both with the drilling and the piping into the building is about $400,000. So we're looking at about 40%. So it's going to be the 30 plus the domestic to get us another 10% that we'll be putting back in ultimately as an incentive to put back into the project. That is what we've found time and time again to make these projects either go or not go, and that extra 30% is really critical, as George and Steve were both saying as well. Educating our clients. Yes, we also used a tax, someone who is very familiar in how to leverage the tax incentives on the OnLogic project, and we'll likely be doing that here at the ILSI Library as well. So, as I mentioned, it is a science experiment, so allowing your clients to understand that it's not magic. We don't know if we're going to hit X gallons per minute at X feet. So in having the driller provide us a budget that's an allowance. So it's like we're going to assume we're going to go down 500 feet per well, and that's our baseline assumption. So you saw that first well was 585 feet. So that's something that we need to, pay extra for. And we had to fill this void with cement. We didn't anticipate that. But then the second well was only 383 feet. So you sort of do that, again, it's like allowing yourself to be flexible, making sure that your client understands that we need to have some contingency planning. And then Steve had mentioned some of the points about containing the slurry. So different sites like OnLogic, wide open, very simple. That was sort of the opening image that I had. You have a slurry pond, if you will, as you're pumping to then collect that sort of silty water and so on. Here, borehole number 1 at ILSI, we're surrounded by pavement. So that was tricky. Just having that planning in place was super important. So here's the diagram that was provided by Steve Ravel. Now these are subsurface fracture lines in the bedrock. So essentially what Steve likes to say is X marks the spot, and if you can get 3 fracture lines intersecting, that's even better. But ultimately, we don't want to move those. He identified 6 potential well sites. We only needed 2 production and then 2 injection wells. So ultimately, he prioritized them as well, 1 through 6. So we started with well number 1. But again, ultimately, it was these are the ideal locations based on those fracture lines. That's where you're going to get the most predictable and reliable water flow that you can count on. These are some of the obvious things that lessons learned. Confirming existing utilities, that's a no-brainer, but sometimes the X marks the spot is exactly where the gas line or the water, existing infrastructure is. So how do you navigate around that? And that's just the back and forth with Steve Ravel and the drilling crew. The capture, the slurry capture I mentioned, It also helps, especially in a location like Middlebury, where we obtained some of the boring locations, say from the town office project or the bridge. Again, it just gives the team a better understanding of what the nature is of the adjacent underlying bedrock. Time of year is important, obviously. You don't want to be drilling ideally in the winter with the slurry freezing and so on. They do it, but it's just more hassle and so on. I recognize that you're not going to read those, the small print over here. This is very simplified diagram of Ilsley Library, so it took the roof off. And, as Steve and George had described, this is a pretty basic open loop system. The 2 production wells are down at the bottom of the ramp, sort of adjacent to the lower level parking. Some of the logistics, we have to communicate with the town, communicate with the butters. This is an interesting, we did the first well, the production well. Then we flipped to the 2 injection wells. And one of the main reasons for doing that, and the injection wells were up on the upper parking lot. One of the primary reasons was that we could take that drilling slurry and then put it back into the production well. So it was a really simple way that Spafford ended up handling that particular. So it was an interesting little workaround, if you will. So similar thing, heat exchanger, and then that goes to a supply line that runs through the building, supply and return, to a series of heat pumps that are located throughout the building. Pretty straightforward, pretty simple system, if you will. That's what I would describe that as. Just going through the numbers is so. Production well number 1 at the bottom of the ramp, as I mentioned, 585 feet, 100 gallons per minute. Production well 2 was a total home run, 383 feet, and that was 250 gallons per minute. So that alone, that one well alone is more than enough to supply our whole building. But ideally we've got this backup. Should anything happen to the pump or whatnot, we've got that as a backup. So, and then up on the upper level, the 2 injection wells. The first injection well, 1,025 feet, and that was 55 gallons per minute. And again, it's as George had mentioned, sometimes a site doesn't work because you can't get the water back into the ground without having a massive pump to force it. So that was one of the reasons why the team decided to move it up to the upper level to get that pressure differential, and that really helped us quite a bit. And then the last injection well was 950 feet. So again, as you're budgeting, it's based on 500 feet for 4 wells, and you have the sort of plus and minus of where do you land. And those decisions you have to make those decisions as the driller is drilling, so you really can't come back later. I'm not going to go into the OnLogic project. It's fairly similar. What's really exciting about this project, and I think it's very consistent with most, is that when you have a client that's already predisposed to wanting to address climate change, reduce carbon, have a super energy efficient building, it just makes our job so much easier. Then we just need to work through all of the cost implications. As George mentioned and Steve, the cost for mechanical systems already was roughly 30% of the overall project cost. It's just become really, really expensive. So any help that we can get in those incentives really especially makes a geothermal system viable. With that, I'll turn it over. Thanks, Alice.
Thank you. Okay. Yes. So, Debbie New. Debbie is a teacher and anthropologist by training. She grew up in Burlington and raised her family in Waitsfield. And in 2022, she launched Vermont Community Thermal Networks to advance thermal energy network solutions in Vermont with a focus on relieving energy burdens, enabling local control, which I think is important, and maximizing community benefits. So previously, she had experience coordinating coalitions and working groups dedicated to decarbonization of the thermal sector, including research and educational initiatives on gas safety, hydrogen, and biomethane. So her approach to thermal energy networks, which she's going to be telling you about, is based on her experience of the power of community organizing. I have to mention, before I turn it over to her, her past role working as a volunteer coach, trainer, and organizer for Mothers Out Front, which did a lot of mapping and pressing for repair of massive gas leaks in Brookline, my old hometown. So very great. So Debbie.
Thanks. I'm glad you mentioned Brookline because I coached that team and they did great stuff.
They did great stuff.
Yeah, but working on gas leaks issues in Massachusetts led me to working with people who were trying to get gas companies to deliver thermal energy through water in pipes, not gas in pipes. And when Alice mentioned hydrogen and biomethane, those were things that we were proving were not appropriate solutions in the thermal sector. So I just wanted to clarify about that. So I'm really glad to be here today representing Vermont Community Thermal Networks and a whole lot of work going on around the state on how we can do the kinds of district systems that have been mentioned already today, but that we're calling thermal energy networks. I don't know about you, but my head is full of stuff about geothermal and drilling and all sorts of heat pumps associated with this. We're going to shift a little bit to focus on communities and what communities are doing. Let's start with Middlebury. In Middlebury, you have a thermal energy networks working group that is made up with a lot of people from around here, mainly volunteers, but also we have members of the Energy Committee, the Regional Development Corporation, the Regional Planning Commission, and as I said, other local leaders and just people who live here who want to see some solutions happening. So some of those people are doing this as part of their work, and some are volunteers, and many are in this room. So thank you for your work together on this. What we've done so far here in Middlebury is we held a community workshop last year. We've done a lot of outreach to businesses and organizations. We've had some site visits. On the lower left, you can see the wastewater treatment plant visit that we had. I recommend that for everyone. And then on the left is the Middlebury Food Co-op, but we've been other places as well. We've also held neighborhood meetings because we've identified in some areas, and I'll talk about this at the end, where there are enough people and enough reasons to consider a thermal energy network. So we've gotten those people together to try to define a project and think about who can own and operate it and how we can finance it. And also I want to do a big shout out to your Regional Development Corporation that's represented here with us today because they won a Vermont Council on Rural Development's innovation grant that has allowed us to hire some expertise that we've needed in order to advance this work. So thermal energy networks are becoming much more of a household name these days, but not many people know what we mean when we say a thermal energy network. So we've heard today about geothermal projects that can be developed for single buildings of all kinds in many locations, and that's great. But we can also connect buildings when they're close enough together to get more out of those ground source heat pump systems and those pipes underground. So it's the same components as geothermal in a thermal energy network. You often would have a bore field to include heat from underground, then you'd have the heat pumps inside, and you'd also have horizontal pipes that would connect buildings to each other at about the depth of a water or sewer line. So just thermal pipes in the same kinds of trenches that we're familiar with in our towns. Whoops. So the other thing about thermal energy networks is that they're not just geothermal. In fact, they're much more efficient and cost effective when they incorporate other kinds of heat. We already produce and waste a lot of heat in every community from many buildings. And one of those sources is ventilation systems and large refrigeration. So there are big pieces of equipment on roofs and behind buildings, and you don't normally see this happening, but there's heat coming out of a lot of different kinds of buildings, just into the air. So you can see here the kinds of buildings that are creating a significant amount of waste heat from refrigeration and ventilation, such as a grocery store that has to cool a lot of things down inside, the refrigerators, the freezers, and so they have to reject heat in order to make it cold inside. Same as the ice arena. So those are places to look for when you're thinking about what kind of heat do we already have that we could recapture and reuse. And there's another kind of heat that I have to admit is my favorite, heat from wastewater. So think about the water that you use, just you, every day, much of which you likely heat up and use and then flush down the drain. And then think about all of our homes and businesses and industrial processes that are doing the same. There's a massive amount of heat that is leaving the Middlebury wastewater treatment plant every day. It comes in and it goes out, and I'll talk more about that plant in a minute. We've visited that plant, and there currently are plans in process to do some upgrades there, which is the perfect time to think about heat recovery, and I believe that is part of the plan, at least to reuse heat at the plant. But the question is there more heat than is needed there that could be shared with buildings nearby? So that's something for people in Middlebury to keep their eye on, and I believe that the Energy Committee is a big part of making sure that that's considered. But any building can contribute heat from its wastewater, and we don't have to have a wastewater treatment plant that's close enough in order to do that, because we can access it at the sewer line or even as it leaves the building and put that energy back into the building to create more hot water, for example. So the great thing about the ground source heat pump systems that we've been learning about is that they can be looped and networked. And we don't have to do huge projects to make this worth it. We can start small with a few buildings, because buildings have different thermal needs at different times. And so by sharing heat between them and balancing the thermal loads, we can get a lot more out of the heat that we already have. And by expanding the system over time, it gradually will become even more efficient and therefore more cost effective. It also becomes more, not just more affordable, but also more accessible, because this is a neighborhood scale solution. It's not one building at a time. It can be available for other people, businesses to connect to it. And this is what it might look like in a Vermont town. So you've got the supermarket and its waste heat going into the network. You can see the buildings are contributing heat from their wastewater. And in this case, the geothermal bore field is under the town green. So it's been drilled, reseeded, covered over, and you don't even know it's there. There are other sources of thermal energy, like from solar panels, and there are a lot of interesting ways to do thermal storage as part of these systems. So a thermal energy network isn't one thing or another. It's a tool that we can use to make use of the heat that we already have, including storing it for when it's needed. So where does this make sense in Vermont? Vermont's a rural state, right? Well, it turns out we have a lot of density in our towns and cities. So that is the perfect place to look for sources of thermal energy from different kinds of buildings and different thermal loads that can be balanced. And we can also start small, as I said. This is a map of Vermont that was surprising to me. It was put together by a couple of regional energy planners, and they identified places where thermal energy networks have some potential in Vermont. So places that are designated town centers, that have intentional growth areas where we need to expand anyway, new housing, new construction, new availability for businesses, and then industrial and commercial parks. I didn't know that there are all these places that we could look at. It doesn't mean that a thermal energy network is going to work in all of these places, but it points to the fact there's something there in more places than you might think that's worth exploring. So just to review, a thermal energy network uses heat that already exists across a community. In many cases has already been paid for, is otherwise discarded and can be used efficiently. And efficiency is something that's come up here already today. We've heard about air source heat pumps, we've heard about ground source heat pumps. This is how I like to talk about this. With an air source heat pump, and again, we need air source heat pumps in many of our buildings, an air source heat pump draws from the outside air, which sometimes is very cold or very hot. That means that they need to work harder to get to what's comfortable for us inside, and therefore use more electricity. A ground source heat pump instead draws from underground temperatures that in Vermont are an average of 50 degrees constantly, year-round. That's a lot closer to what we want inside our homes, winter or summer. And if you're adding waste heat in the network, you could be using 70-degree water to get to a nice 70 degrees inside, because that's the kind of temperature you can get from waste heat and from wastewater. So the less electricity we have to use to meet our thermal needs, the more we have electricity for EVs and the air source heat pumps we need in certain locations, and we don't necessarily have to build out the electric grid as much as if we tried to electrify everything. So by using local sources of thermal energy, we don't have to pay as much for as many wires and poles in order to meet our thermal needs. The thing about a thermal energy network is that it's shared infrastructure, a lot like our water and wastewater systems that many communities in Vermont already have. They're familiar. Water and sewer systems are public infrastructure that do a lot of things for us. They allow developers to build without having to do that for themselves. They save money, they increase property values, and they encourage denser, more walkable mixed-use communities, which in turn are perfect for thermal energy networks. So municipalities know how to do this. They install these systems and provide these services. They have access to lower cost capital to cover the upfront costs, and customers paying regular bills over time can help to repay that cost, that investment, and also fund operations and maintenance over time. So, a thermal energy network is similar shared infrastructure that does a lot of those same things. Water and pipes serving many buildings at once can be locally owned and can be installed, operated, and financed in the same way or in very similar ways to what we do with water and sewer. In fact, the economics of a thermal energy network are exactly the same, if not better, because the water in the pipes doesn't have to be treated or maintained as intensively as for potable water and for sewer. So these systems could, in many ways, be easier. This brings us to the fact that thermal energy networks could support new housing development, and the state has mandated housing targets that regional planning commissions have identified numbers for each town. So each town in Vermont now has already received or will soon be receiving a number for the amount of new housing they need to add over time. So thermal energy networks can help with this because we've already said they're most cost effective where we already have density and we already have a lot of heat, a variety of thermal resources and needs. So they make sense where we need to add density and new housing anyway, and they can contribute to our smart growth goals. The thing about thermal, I just want to pause here because I had taken out a slide just to try to make this a little shorter, but because the Inflation Reduction Act incentives have been mentioned, I want to suggest that especially for new housing, if we can hold on to those incentives, and we have a man in Washington who is there every day lobbying for the geothermal industry to keep those incentives for all of us. If we can hold on to those incentives of 30% off a system or 40% off if you're using domestic manufacture, and in this case, almost everything is built in the United States, we could get to 40% off. So if you're putting in water or sewer or trenching something anyway for new housing, if you add a thermal pipe to that, the entire trenching can be covered by the Inflation Act reduction 40% off. So you can get a lot more mileage out of putting thermal energy into a housing project with the water and sewer that way. So there are a lot of reasons for local ownership, for local development and local control of a thermal energy network. And just because of time, I'm going to focus on one of those, which is that a thermal energy network is a civic asset in that it doesn't have to be funded by taxpayers. A thermal energy network creates revenue because it's not like a bridge or a road, unless you put up a toll booth, where the taxpayers have to pay for it and then people use it, but they don't pay money for it, unless you decide you want toll booths in Middlebury or Addison County. A thermal energy network would be paid for by the customers paying their bills, and that's the revenue that could pay back that upfront cost over time. And if you're a town taking advantage of your wastewater heat, you can also earn money for contributing that heat into the network, and people can pay for the heat from your wastewater treatment plant, generating revenue that can support the town and be invested locally. So we've heard about Champlain College in Burlington, we've heard about Hula and other examples of where this kind of districted or network system works, but I want to talk about Iowa, because West Union, Iowa has had a municipally owned, locally controlled thermal energy network going since 2012. Now, I've explained this, this case study to other people in the room already. I can say more, there's examples on my website, but what I want to share with you is that we've been talking with them, learning from them, and we're going to go visit them in early July to see this in person. When they wanted to set this up, the town said, we want nothing to do with this. So the group of businesses around the town green, where the geothermal was going in anyway for the courthouse, said, we'll do it. They created a member-owned LLC, which functions pretty much like a co-op. The town owns the outdoor systems, and it leases it to that group of businesses for $679 a year. So they've been working on the system, adding businesses to it over time, and they have been lowering customer costs gradually over time. This year, because they're starting to earn revenue from the system, they issued dividends to all of their members, like a co-op would. So this is an example we can consider. So let's talk about what is being explored in Vermont. So when we start to develop a thermal energy network in a town, we look first for where there is already heat. We look for the thermal energy resources. And you can see there's a commercial bakery, an ice arena, a grocery store, a brewery. We've talked about that, those kinds of examples. There can also simply be a geothermal bore field that gets shared. Then we look at what are the buildings nearby. And it's often housing or the need for new housing, but it's also municipal buildings that can benefit, a library, a town hall, also a lot of other places that people in the community rely on, and that also often provide community services like a church or a health center. And then we find other buildings that could be added in over time. Again, you can see housing, but there's also pizza, another brewery, because we have a lot of breweries, a school. These are places that may have excess heat that can also go into the network, making it even more efficient. There also happens to be more than one place where there's a new anaerobic digester that happens to be near a factory and possibly a wastewater treatment plant. And yes, I am talking about Exchange Street, but I'm also talking about St. Albans and maybe even Enosburg Falls. So there's a lot of heat in those places that could be shared. And last slide, this is Middlebury and what we're looking at here. So just briefly, on the left is Exchange Street, and numbers 2 and 3 at the top, the anaerobic digester and the factory, could share heat between themselves. We've looked at this, we've talked to them, they're interested, and then the wastewater treatment plant is there as something the municipality might want to add at some point. There are a whole lot of other businesses there that need heat, that generate heat, that could be producers and customers, or both, for a network. So that's a really interesting area of town. There's also Washington Street. And on either side of Washington Street, you could have a network separately without having to dig under the street and disrupt traffic. So eventually, over time, you might decide you want to connect those two networks. But at the top, you've got a food co-op, you've got a bagel place, you've got an inn that has a couple motel buildings that would be easily connectable, and also affordable housing in Peter Cove Village, not far from where we are right now. Across the street, the bank is connectable. There's another grocery store, an ice arena, a school, a courthouse. So there's lots of possibilities there as well. And the people that I mentioned at the top who are working on this continue to explore this, and we'd love to have your questions, and love to have you join us, and we hope we can get a thermal energy network in Middlebury before too long. Thank you.
Thanks. Thank you so much. This has been super information-packed. We're actually close to finishing time, but do people have pressing questions that they want to ask to this group? I know it's a long time to sit in space. I can tell. Yes, go ahead.
I'm curious about barriers to adoption. If, for example, thinking about technical barriers or institutional barriers or social behavioral barriers, what do you all see are the primary impediments to adopting this technology more broadly?
I'll just start. I think the barriers are quite broad and wide, and I think that educating your clients, that's our job as architects, engineers, and builders, to present the case studies that demonstrate the financial picture, because there's always concern about that. That's never going to go away. You know, the technology is always changing, as we discussed earlier. So I think it's presenting to our potential clients the opportunities, frankly. So I don't know. I see it as opportunity versus barrier, with the caveat of 30 to 40% off to make these systems really economically similar to baseline code, you know, fossil fuel based systems. That would be my take.
I would just add that there is money that might not be too hard to access once you have a project, but all of the development work that volunteers in this room and other people are doing in the state of Vermont is often not funded. And so it's hard to get the expertise we need in order to move projects forward.
I think the financial barrier is the biggest one. It's not hard to overcome, but I had to swallow hard and say, I gotta raise some money. And otherwise it's coming from our bottom line, and our bottom line has a different mission, right? So, but it worked out.